when we have a series,
Are you recording?
yes,
Okay.
circuit, a series circuit exists when we have a power source, a connecting pathway, multiple resistors that are all in one continuous loop and getting back to the power supply. So this would be a series circuit in which we have three resistors all in series. This is a 12 volt battery, that's a 10 ohm resistor, and a 20 ohm resistor, and a 30 ohm resistor, and this will get us beautiful results. Now, we find that in a series circuit, since there is only one conducting pathway that goes around the whole thing, then what happens is the current has to be the same everywhere. Because it's impossible to shove charge around the circuit and have a different amount go through the 10 than goes through the 30. Since there's only one pathway, the same charge has to go through all of them. So the current is going to be the same everywhere. But the voltage is what's doing the pushing of the current around the loop. And since the voltage is pushing this, the different resistors are going to take a bigger chunk of the voltage. So the big resistor takes the big chunk and the small resistor takes the small chunk. So the amount of voltage that you get, we call the voltage drop. How much is the voltage drop going through that resistor? So the voltage drop is proportional to the resistor. So the small resistor will use the least amount of voltage and the big resistor will use the most voltage, and that kind of makes sense. It's kind of like if you're playing tug of war against three people at the same time, you're really fighting against the strongest guy, the hardest, right? So it's similar there. Yeah. So you will end up using the total voltage all the way around. Now, we have this concept that's called effective resistance. RE is known as the effective resistance. And the effective resistance is basically what, if we could replace these three resistors with just one resistor, how big would that be? That's effectively what the effective resistance is. So to find the effective resistance when you're in a series circuit, we're just going to add them. Super duper easy. And then find everything else out. All we're going to use is V equals IR. Really tough stuff, right?
Yeah.
Okay, so first thing we want to do is find effective resistance. So how am I going to find the RE? I'm going to add them. So I'm going to say 10 plus 20 plus 30 equals 60. Hooray! Boy, step one was tough. Step two, we want to find our current, which will be the same everywhere. So if we want to find our current that's going to be the same everywhere, we're going to say the total current equals the total voltage over the total resistance. So the total current would be the total voltage over the total resistance. So our voltage here was 12 volts, and we divide by 60 ohms. That gives me 0.2 amps of current going through this circuit. Super duper easy. Next, we want to find how much of a voltage drop do we have going across each one. Now, we're going to lose 12 volts around the entire circle, but we're not going to lose an equal amount of power on three of them because they're not equal. So, next we want to find our voltage drop. And V drop equals I times R. But here we don't use the total R, we use just the individual R. So how many times do we have to do step 3? 3 times. So the I is going to be the same all 3 times, but the R is going to be different all 3 times. Now, if you do this correctly, your total voltage drop going around the whole circle should add up to whatever your total voltage was, which it does in fact do here. Now, I gave you nice perfect numbers here that round off beautifully. Sometimes you get numbers that don't round off so beautifully, and because you like to round, sometimes when you get to the end, it'll seem like there's voltage left. There's not really voltage left. In electricity, electricity doesn't round. You round because you like to stop your numbers at some point, but electricity doesn't do that. So it will always be proportional like that. So then we get to the part where, like, say this is wire A and wire B and wire C and wire D. Now, if we want to know what is the voltage in the wire, when we first come out of the battery, the voltage is full voltage. So if I would connect a voltmeter here and connect that to ground, this voltmeter would read 12 volts. If I would connect a voltmeter at B and connect that to ground, that would read 10. If I would connect this one to a voltmeter and connect that, there's another way to make a ground symbol. It can also look like a little rig instead of a pointy arrow thing. But you see, if I connect C to ground, then that voltmeter would read 6 volts. And if I had a voltmeter connected to D and connected to ground, it would read nothing. Now, how did we get these numbers?
The resistor.
Yeah, if you were paying attention earlier, we said we got a voltage drop. And so we said, how much did the voltage drop here? 2. It dropped 2 volts. So if we start off with 12 volts and we lost 2 volts, how much is left? 10. So how much voltage did we lose in the 20 ohm?
4.
We lost 4 volts. That's why there was only 6 left after that. And how much did we lose here?
All of them.
6 volts, which means when we get down to here, we're going to have nothing. That make sense? Are these easy lemon squeezies?
Are we caught up?
That's it.
I got a lamp.
This is roughly a third of what we're doing today. Yeah. So
How is this a lamp?
this was the series circuit.
Parallel.
Now we got to learn
Oh, the 1 over R1.
parallel.
Mr. Paulson, how is this a lamp? No. That's dumb.
It's not dumb.
Can't you make the reason
Looks like a-
Which is weird, right? A lamp is another name for a bulb.
A lamp was like
It doesn't have to be like. Okay. Anyway, back to what we're learning. This is one type of circuit, the series circuit. Another type of circuit is called a parallel circuit. And a parallel circuit is similar to a series circuit because they both have multiple resistors, but the multiple resistors are lined up differently. So we're going to have the exact same resistors and the exact same power source, but we're going to hook them up in parallel. If we hook them up in parallel, now we have multiple pathways to get back to the battery. So this battery is still 12 volts, that's still 10 ohms, this is still 20 ohms, So 30 ohms. So we have the exact same ones. Now, do you see how this is multiple pathways?
Yes.
Here, if I come out of the battery, I can go through 10 and get back, or I can come down and I can go through 20 and come back, or I can go all the way down and go through 30 and go back, but I don't have to go through all three to get back to the battery. So, since that's the case, then it's not going to be the current that's the same everywhere. What's going to be the same everywhere is the voltage drop.
Total voltage.
Yeah, so the voltage drop is going to be the same in each branch, and that's going to equal the total voltage. Because I'm going to lose all 12 going through each resistor. Now, last time the voltage drop was proportional to the resistor, but here the current is going to be is inversely proportional to the resistance. So the big resistor will have a small current, and the smallest resistor will have the biggest current. And to find the effective resistance here, instead of just adding them, we have to add them with the 1 over R rule. So we're going to have 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. What? Branch. It says branch. When my oldest daughter was little, and we would go to the ranch, she would always say, "We're going to the branch." I don't know why. But she had a friend who had a ranch, and we'd go out there. We're going to learn about that after we learn about these.
We're gonna get like triple parallel circuits.
No. Okay, so first we're going to find out what our effective resistance is. To plug this in and make the algebra super simple, we just cheat on our calculator, and we look for a button on our calculator that says x to the minus 1. It is located right above where it says squared. Everybody see it?
That's cheating.
Okay, so the x to the minus 1 button, what it does is it takes the number that you put in there and it flips it inverses, just like it says here. But how many 1 overs do we have in this formula? There's 4. So how many times do we have to hit this button?
4 times.
4 times. We hit 3 before we hit the equals, then we hit the equals, and then we have to hit it once at the end. So you're going to write down 10 to the minus 1 plus 20 to the minus 1 plus 30 to the minus 1. Then you're going to hit equals, and that would give you 1 over RE, but we want RE, so we have to hit x to the minus 1 at the very end. After you hit equals. Don't hit it before you hit equals, and that will just undo your 30.
So you hit it before it.
No, this is to find the RE. So the effective resistance here is 5.454545 ad nauseum ad infinitum.
4, 5.
It keeps going forever. Forever.
Wait, are you recording this?
This has only been a test of the emergency broadcast system. Okay, so how do we find the current? we find the current just by doing I equals V over R. The V is always going to be the total voltage, and the R is just going to be the individual resistor, because these act like they're separate. So we're going to have 12 over 10. That's going to give us 1.2. And then we're going to have 12 over 20. So this would be 1.2 amp. But this is going to be 0.6 amp. And then we're going to have 12 over 30. And that's going to give us 0.4 amps. So that's how much current is going to go through the 10 and through the 20 and through the 30. Super duper easy, right? What? Okay, 0.4 amp is going to be how much current goes through all of that green wire, right? And 0.6 is going to be how much goes through just this branch. And 1.2 is going to go how much goes through that branch. But how much is going to go through this one or this one? That's going to be 1.0, because this one has to carry the current that goes through this loop and the current that goes down. Both of those go through this section, right? So if we add up those two numbers, that gives me 1. So how much total current goes through this section?
1.8.
That has to cover the 1 and the 1.2 that's branching off this way. So this has to have 2.2 amps in total. And conversely, over on this side, they all branch together again. And so this one also has to carry all of that current. So the total current in the circuit is 2.2 amps. So if we take the total voltage and we divide it by the total current, we should get what the total resistance is, right? So if I take 12 over 2.2, that gives me 5.45454545. So you can either figure it out the hard way or you can figure it out the 1 over x way, and it comes out the same way. And that's a good way to double check yourself and make sure that those work out the way that they should work out. Now, I just want to pause, and this isn't how to solve the problem, but I just want to pause and show you this. If we look at power, P equals IV, right?
Yes.
What was the total current in the series circuit?
On the series?
The total current in the series circuit was 0.2, and the voltage was 12. So the total power used by this circuit was 2.4 watts of power. Now when we hooked it up in parallel, our total current was 2.2 amps, and it's still 12. So 2.2 times 12, 26.4. Is that a large jump?
Yes.
Yes, these are the exact same components, but when we hook them up in parallel, we use a lot more power, which means if these resistors were light bulbs, then over here they would be very dim, and over here they would be very bright, because they're using much more power. So if you hook things up in series, it's lower power. If you hook them up in parallel, it's higher power. It's all making sense? Super simple, right?
Yes.
Okay. Are you ready for the series parallel combination?
Yes.
What do you mean no? Oh, we hear that head rattle this way, not that way. Okay, so now we get to draw a very pretty circuit. That's going to be a series parallel combo circuit.
Oh, no. My brain.
Your brain already hurts?
I'm never supposed to.
We haven't even
You're hacking.
started hard yet.
Is that Batman? Is that a robot?
Yes, this is a circuit drawing of a robot.
Batman's a robot.
Play that.
You realize I should have retired a long time ago, right?
But then you wouldn't have this.
Exactly.
Well, that's messed up.
You're like,
You would.
oh, my God. Well, does it take art class?
This is an art class.
No, no, no. Wait.
I was gonna move it over a bit, but it didn't take everything, so.
When did you get this marble?
I don't know. Years ago. Why?
When I was there, when they first installed it, like, I don't remember what grade I was in, but I was like, whoa. But like, no other teacher would use it. No empty space.
I like smartboard.
It's only good for the teachers that know how to use it.
Well, I know how to use it, so. I like being able to draw it and erase it and not getting junk all over everywhere. And I like being able to record on it. And I like being able to do my presentations and then just draw on them. And
What's the middle interval between?
okay, so this one says 10, and these are both 50s, and then we have 100, 200, 300, and then we got a 35, 25.
Impossible.
It's impossible.
Is it a trick question?
It's impossible. Okay, so we clearly have several parallel branches that are in series with each other, and in series with one resistor.
What?
So how in the world would we attack a problem like this?
You don't.
Cry, curl up and cry.
You curl up in a fetal position and cry.
Give it to professionals.
No, you little wuss.
Give it to you, the self.
Change majors.
Is one side 35 and the other side is 25?
Yeah.
No.
Change majors and go somewhere.
First, we want to redraw it like it's a series circuit. And you say, why? Why? Because that's the easiest way to do it. So the first one is, and what we're going to do is we're going to just pretend
Combine.
each parallel branch is one resistor.
Also, you add them up the resistors.
So we're just going to pretend each parallel branch is one resistor. Well, this one was just 10 ohms to begin with, so that one's easy.
And then you can add over.
But if we have two 50s in parallel, they act like a what?
100.
Not like
1
100,
over-
that would be if they were in series.
1
They're in
over 50.
parallel.
1 over 50
So
plus.
you have 1 over 50 plus 1 over 50 is 2 over 50, which is the same as 1 over 25. So this is going to act like a
25.
25 ohm resistor. Now if I have 100, a 200, and a 300, that's harder to do in your head. So we'll just use a calculator. 100 to the minus 1 plus 200 to the minus 1 plus 300 to the minus 1 equals to the minus 1. And now we get 54.5. It's still the same number we were dealing with last time with just zeros. So here we have 54.5. ohms is that resistor's equivalent. And then we take a 25 to the minus 1 plus a 35 to the minus 1 equals to the minus 1. And this one becomes 14.6 ohms. Capiche?
Yes.
What?
Yes, go fishing.
Go fishing. Okay, so now can we find out what the effective resistance is?
Yes.
Sure, the effective resistance we just add around the circle. So if we take our 14.6 and we add our 54.5 and we add our 25 and we add our 10, we get 104.1 ohms in total resistance. Isn't that fun?
Yes.
Okay, so then we can find the current, right?
Yes.
So I, of course, is equal to
V over R.
V over R. So we're just going to have our 75. This is 75. That's a beautiful 5. 75 volts over 104.1. .72. 8. So we got 0.72 amps going through everything. Then we want to find our T drop. So we're going to have our 0.72 times 10. And we're going to have 0.72 times 25. And we're going to have 0.72 times 54.5. And we're going to have 0.72 times 14.2. I can do that first, but it's in my head.
Oh, me too. 7.2. Move the decimal.
The rest of them, I'm more brain dead. Now, if I add these up, what should they add up to?
75.
But they won't.
Because we rounded.
Because we rounded. But 7.2 plus 18 plus 39.2 plus 10.5 equals 74.9. And do we say that's close enough because we just rounded? Yes! Okay, so that looks good. So far, it looks good. Now, that means, again, we lost across this section, we lost 7.2 volts across this resistor, we lost 18 volts across this resistor, we lost 39.2, and across this resistor, we lost 10.5 volts. But only one of those resistors actually exists.
10.
The 10. But when we go back to the original, this 10 ohm resistor, we know it had a V drop of 7.2 and it has a current going through it of 0.72 amps, right? And then we go back to the 50 and the 50 and we say, hey, I know the total current going through the whole puppy was
Divided.
0.72, but since they are equal resistors, then we would have an equal amount of current going both ways, right?
Yes.
So the current going through each one would be half
Yeah,
of 72 is 36,
36.
so 0.36 amps. And the voltage drop across this section was 18 volts, so it'll be 18 volts on both sides. What? Because, do I go through both of them?
Yes. Yes.
No.
Oh no.
If you're a chunk of charge, you're either gonna go this way or you're gonna go that way, but you're not gonna go both. So again, the voltage drop in parallel is gonna be the full voltage for that section across any resistor you go through. So it's gonna be the same, this is gonna be the same for both sides here.
Even if they're different.
Now, even if they're different. Now, the voltage drop across this section we said was 39.2. So it doesn't matter whether I go through the 300 or the 200 or the 100, I'm gonna lose the same amount of voltage either way. And you're saying, well, if it's the same voltage drop either way, then aren't they all the same? No, because who's gonna have more current going through it? The 100. Now, what we could do is set up a proportional thing, but the easiest thing to do to find the I is you're just going to say I is V over R. But the V here is going to be the voltage drop in that section, not the total voltage drop. So the V drop is going to be 39.2 over 100 and 39.2 over 200 and 39. Come on. Over 300. So what should all three of these currents add up to? If you have 0.392 plus 0.196 plus 0.131, that adds up to 0.719. I can write and talk at the same time. 719. Hey, what's it supposed to add up to? That's close enough, right? Okay, because again, we said the total current going through this wire was 0.72, so if it branches three ways, those three ways still have to add up to the total, which they do. So then we get to the last section, and what's the V drop in this section? 10.5. So here we're going to have 10.5 over 25 would be the current on this side, and then 10.5 over 35 would be the current over on this side, and those two answers should add up to 0.72 again. So we have 0.42 amps on this side. And we get 0.3 amps on this side. And 0.3 and 0.42 add up to 0.72. Isn't this exciting?
Yes.
So then if we're taking a little trip and I say, okay, I'm starting off and I'm going through this one, I'm lost 7.2 volts, and then I either went this side or that side, I can't go through both, and then I have to go through one of these, and then I have to go through one of these. How much voltage did I lose all the way around?
75.
A total of 75. And again, because I'm not doing little laps, I'm not going ham, you're going through one or the other. So the voltage drop around the circuit is still going to be 75 all the time.
Which is more effective, that one or the power? Or like in terms of power, which one's more effective? That the series parallel or just parallel?
Well, this just has different power than straight up parallel is always going to give you more power than here because each of these you're pumping again. Yes, dear.
Why would you use, what's the different uses of them?
What who, how?
The different uses. Why do people use parallel and why do people use
Like
More
what
power.
we did with it.
More power.
It has to do with how you want things hooked up. Like
With
if
these ones.
if you want it to be a limiting thing, like back in the old days, they used to hook up Christmas tree lights in series because we had these bright bulbs and they would use up a lot of power. But if I hooked a bunch of them up in series, then they would use less power and you'd be less likely to burn down your tree. That was because they couldn't make little tiny light bulbs. But then once they figured out how to make little tiny light bulbs that didn't generate a whole lot of heat, then you can just hook them up in parallel. But the old days, you had to hook them up in series so that they wouldn't cook your tree. But that was aggravating because if one bulb went bad, then the whole thing turned off and you had no idea which one was the bad bulb unless you did lots of testing. Whereas when they're hooked up in parallel, the light bulb that goes bad, you just say, hey, it's the one that's not working. That one, it's more complicated because here we're just showing you resistors, but we can hook up other things other than resistors that slow down your current. So you can hook up motors and you can hook up capacitors and you can hook up things. So you gotta basically learn the basics before you can start learning the more advanced stuff, but we're not gonna get into anything past the basics.
Resistor. Variable resistor.
Actually, on the physics 1 test, you won't even have this. You'll have a series or a parallel, but you won't even have combination circuits. So I'm teaching you more than you need to know. What?
The red line that you traced,
Uh-huh.
where you explain,
I was just saying I have to go through this one, and then when I'm coming down here, I can go through either side, but I don't go through both. And then here again, I take a choice of one of these pathways, and I take a choice of one of these pathways. So going all the way around, you don't like add up the voltage of both of these. You just take the voltage of one. So it's still at 75. Yeah. So if you're that little chunk of charge, you're gonna take one trip. You're not gonna.